How's everybody?
Good.
Excellent.
Let me get a drink of water.
Okay.
William Ainsworth.
Here.
Sorry, I had my headphones plugged in, but I didn't have them in my ear, so I didn't hear you.
I'm here.
Caleb,
Here.
Brody,
Here.
Joe Bevilacqua,
Here.
Joe Blakely,
Yeah.
Ryan Burns,
Here.
Drake DeTore,
Here.
Charles DePasquale,
Here.
Martin,
Right here.
Dejor,
Here.
Bobby,
Here.
Bailey,
Here.
Busse,
Here.
Owen,
Here.
Alex,
Yeah, I'm here.
James Johnson,
Here.
Brooke,
Here.
Jack Kenny,
Here.
Elias,
Here.
Matt,
Here.
Mike Mandola,
Here.
Paige,
Here.
Matt Morgan,
Here.
Brandon Morrow,
Here.
Connor O'Brien,
Here.
Matt O'Donoghue,
Here. Here.
Shane,
Here.
Jesse,
Here.
Ryan,
Here.
Zoya,
Here.
Marco,
Here.
Grace,
Here.
Nick, Slattery, Chris Starkweather,
Here.
David Styria,
Here.
Nolan Toft, Sean Wesley.
Here.
Okay. How is everybody today? How's it going over there at St. Bonaventure?
Going great.
No. Who said that?
Me.
Owen, it's going great?
Yeah, it's going pretty good.
Where do you live?
I live off campus.
Yeah, that doesn't tell us all a lot.
I live next to family in a house called UN.
Okay, we all go there, right? He's having a great time.
We're okay with that.
We find out what's going on there. So, we were talking about math review, and I want to continue that today. Before I do, let me ask you about R. Is anybody playing more with R? Because I realize we're like moving, we're taking a little hiatus from R to come back and review some math, which I think is useful. I just think it's useful. You guys may disagree, and I'm sorry about that. So let's look at, let's try and get me to have a useful. I did a couple of things. I'm going to share my screen. Maybe. What do you see? Joe, Blakely, tell me what you see.
Math review slides.
You see my Moodle page?
Yep.
Okay, so I rescanned this so you can read the numbers. How about that? That's better, right? I also made some notes on individual slides that I thought were kind of important. So when we get to them, I'm going to swing back and forth between the slide and the notes. Okay. You guys hear that?
Barely.
Okay. Okay. So we started talking a little bit about doing derivatives, right? And basically all I want from you is that you know what the derivative is and how to calculate it. And for the most part, it will be a something simple and it will be a first order derivative. Okay? So the basics. Come on. God, help me. We did this. The derivative of a constant is 0, right? So y is equal to 10. This is just a horizontal line, right? Y is equal to 10. A linear function is just its slope, right? So 3x, the derivative here is simply 3. Nonlinear functions have different gradients at every single point, at infinitesimally small points if we were actually taking a math class. Gradient in each point is equal to gradient of the tangent. So that's how we do this, right? We want to know the tangent at this point. That tells us the slope of that point at that particular point, right? That value of x. So this is the derivative of a power function n of x, i.e. y is cx raised to the n. The derivative would be c times n times x raised to the n minus 1. So if y is equal to 4x cubed, the first derivative would be you bring the 3 down and multiply it by the 4 and take 1 away from the exponent. So it's 12x squared. Yeah? So the derivative of a sum and the derivative of a difference. Now look at. You can see this slide. Joe, you're my man to tell me what you can see. You can see this slide, right?
Yep.
Can you see the whole thing?
Yep.
All right. Now do you see my notes?
Yep.
So we have slide 29 that we were just looking at. I want to talk a little bit about it. The derivative of some function y is equal to cx to the n, which can be written f prime of y, which is the same as dy by dx, is n, bring the n down, times c times x to the n minus 1. In other words, if your function f of y is 3x squared plus 4, the first derivative would be 2 times 3, or 6, x to the 1. Okay? The second derivative then, of course, is just 6. Another example, if your function is 4x cubed, the first derivative is 12x squared. The second derivative would be 24x. Okay? So essentially, that's what I want you to know about derivatives. Derivatives of logs and exponentials, I probably won't ask you, but it's useful to know. Higher orders, I'm not that keen that we bother with this, right? I just want you to know what a derivative is, and I'll tell you why in a minute. Higher orders, that's fine. I don't really care too much. It's the same principle, okay? Maxima and minima, this is why I want you to know about derivatives. So you have a quadratic function, y is equal to 5x squared plus 3x minus 6. The squared term in the equation has a positive sign. The function will have a U-shape rather than an upside down U-shape. And we'll have a minimum rather than a maximum. So the first derivative of 5x squared plus 3x is going to be 10x plus 3. The second derivative is just 10. Because the second derivative is positive, the function indeed has a minimum. To find where the minimum is located, you take the first derivative and set it to 0 and solve for x. So, since we have the first derivative here, 10x plus 3, you can solve for x here and say that's negative 3/10. If x is negative 3/10, y must be negative 6.45. Therefore, the minimum of this function is found at this point. I made some notes on this slide, slide 33. So I just do the same thing that they do on the slide. Your function y is 5x squared plus 3x minus 6. The squared term is positive, must have a minimum. See slide 7. All right, so you're going to go to slide 7 for 1 second here, okay? Quadratic functions. If c is positive, the function will be U-shaped. If c is negative, it will be upside down U-shaped. So, since the squared term is positive, it must have a minimum. In other words, it's a U-shape. Or you could also say the second derivative is positive. In that case, it would have a U-shape. See slide 32. The second derivative is negative. The function has a maximum. If the second derivative is positive, the function has a minimum. Okay? So to find the minimum or maximum, set the first derivative equal to 0 and solve for x. The first derivative here is 2 times 5 times x to the 1, or 10x, plus just 3. Set that equal to 0, x is negative 3/10. Put that back in and solve for y. 5 times negative 3/10 squared plus 3 times negative 3/10 minus 6 makes y equal to negative 129 over 20, which is exactly this, negative 3/10 and negative 129 over 20. Okay? So you're all saying, Gallagher, why are we doing this? You're making me crazy. I don't want to do this, right? This sucks. But it's important because there's a number of things that are important about this. And I want to do this, okay? See, if we were in class, I would write on the board, but we're not, so I won't. Remember in economics, you wanted to produce where marginal cost equaled marginal revenue, right? So when a derivative is equal to 0, that means that there's no slope. That means that this line changes from downward sloping to upward sloping. That means that's the minimum. So that's important to know how to figure out what that is mathematically. So if this were marginal revenue, you could say we could produce this quantity. Yeah, because that's where we would maximize our profit, right? Where marginal revenue equals marginal cost. Remember that from economics? That's why this is important. What if I said, this is a graph of advertising and sales. Well, you're not going to want to advertise over here, are you? You're going to want to know where that point is, right? Because at that point, you're maximizing your sales. Does that make sense? Do you feel better about learning this, or does it still suck? Okay. Okay, that's maximum and minimum. So you guys remember this because I will ask you. Partial differentiation, I'm not that interested, you know. It's useful to know what it is, but I'm not going to require that we go down that road, you know. How to do it, that's fine. The slides are here if you wish. Integration, it's no big deal for you not to pay attention to these slides. Matrices. I want to talk about matrices because, and I want to spend some time with them because I feel it's important. In financial econometrics, the use of matrices is widespread and very important. So let's go through this. Some useful terminology. A scalar is simply a single number, right? This is just terminology. A vector is a one-dimensional array of numbers. A matrix is a two-dimensional collection of numbers. Matrices are very useful and important ways to organize sets of data. Matrices are widely used in econometrics and finance for solving systems of linear equations, etc., etc. Most notably, portfolio theory. Working with matrices. The dimensions of a matrix are quoted as row by column, number of rows by the number of columns. Each element in a matrix is referred to using subscripts. So you would say R23 to identify the element in the second row and the third column. Suppose a matrix M has 2 rows and 4 columns. This would be noted M23, that's the element in the second row and third column. More generally, M sub ij refers to the elements in the ith row and the jth column. So we would have a 2x4 matrix, 2 rows by 4 columns, right? Rows by columns. And they're denoted element 1, 1, 1, 2, 2, 1, 2, 2. You see what's happening, okay? If a matrix has only one, if a matrix has only one row, it's a row vector, which will be 1 by C, where C is the number of columns. Okay, let's get on. This is very exciting. This is very exciting, everybody. So even though you may not think so, I want you to get excited. A matrix having only one column is a column vector, which will be dimension R by 1, where R is a number of rows. Number of rows and columns are equal. It said the matrix is square. Matrix in which all the elements are 0 is a 0 matrix. Symmetric matrix is a special matrix that is symmetric about the leading diagonal so that M sub ij is equal to M sub ji. What does this mean? So a couple of slides ago, I said matrices were denoted by row by column. Slide 40. The symbol upside down A means for all in math. Okay? So this means M sub ij is equal to M sub ji for all ij. So do you see how this is symmetrical along this diagonal, right? We have a 2 and a 2 and a 4 and a 4 and a 7 and a 7 and a 6 and a 6 and a 9 and a 9 and a -8 and a -8. So it's symmetrical. The diagonal matrix is a square matrix which has non-zero terms on the leading diagonal right here and zeros everywhere else. Diagonal matrix with ones in all the places on the leading diagonal and 0 everywhere else is known as the identity matrix. This is essentially a matrix equivalent to the number 1. Multiplying any matrix by the identity matrix results in the original number being unchanged. Just like if you multiplied 4 by 1, you would have 4. So, in order to perform operations with matrices, they must be conformable, depending on what you're doing. So simple things like addition and subtraction of matrices requires the matrices to be of the same number of rows and columns. The operations are then performed element by element. So matrix A is equal to this, matrix B is equal to this. You can add those, yeah? You could subtract those. The notation would be A plus B, A minus B, even though there's a great big thing going on over here. Dividing a matrix, multiplying a matrix by a scalar that is just a single number. Every element in the matrix is multiplied by that number. E.g., 2a is equal to 2 times all the numbers in the matrix. More generally, the following results hold. A plus b is the same as b plus a plus 0, 0 plus a, etc., etc. Okay? All simple rules. Matrix multiplication. It gets more interesting now. Multiplying two matrices together requires the number of columns of the first to be equal to the number of rows of the second. Note also the ordering of matrices is important. So A times B is not the same as B times A. Okay? Matrices are multiplied together, resulting will be the size number of rows of the first by the number of columns of the second. So this is slide 44. If we were in the classroom, I would be writing this crap up on the board. So slide 44. To multiply, they must be conformable. So this little booklet of notes is up on Moodle for you. In other words, so you can always come back and look at this, right? The number of columns of the first must be equal to the number of rows of the second in order for you to multiply a matrix. The result is that the number of rows of the first, the result is a matrix with the number of rows of the first matrix and the number of columns of the second matrix. Okay? So what am I talking about? How do we do it? You multiply along the rows of the first matrix and down the columns of the second matrix. let's look. There's an example. There's an example right now. The actual multiplication of the elements of 2 is done by multiplying along the rows of the first and down the columns of the second. So we have 1 times 0 here plus 2 times 6 along the rows of the first and down the columns of the second. 7 times 2, no, 7 times 0, 3 times 6. 7 times 0 plus 3 times 6. This becomes the first element in your resulting matrix. This becomes the second element, so this is 1 times 2, 2 times 3, right? 1 times 2, 2 times 3. 1 times 4, 2 times 0. 1 times 9, 2 times 2. And then you get this. Okay? So 1 times 0 is 0, plus 2 times 6 is 12, is the first element. Everybody cool with this?
I have a question. Is there an application in Excel that allows you to multiply and add matrices?
I don't know if there is. I don't think so. Why, you want to use Excel?
That's just easier than doing it by hand.
Oh, yeah. All right. Well, that's a great question. So let's go here. Can you see my screen?
Yep.
Matrix Calc. Matrixcalc.org. So what was the one we just looked at? One 71236. Zero 249 6302. Notice the number of columns of the first is equal to the number of rows of the second here, right? Let's select A times B. 12, 8, 4, 13, 18, 23, 28. Twelve, 8, 4, 13, 18, 23, 28, right? So look at if I did this, right? And then I said multiply. You can't do it. The number of columns of the first should be equal to the number of rows of the second. Does that help, Matt?
Yeah, thank you.
It's a pain in the ass to do it by hand, but I recommend you do it by hand because it's good for your brain. You don't wind up like me. All right, let's go back to work. Very exciting, this. Sorry. Okay, are we back on my, on the PowerPoint?
Yep.
Thank you, Joe. Transpose of a matrix. This becomes very important. A prime or A transpose. The matrix obtained by switching the rows and columns of a matrix. So you see 1, 2, 7, 3, 1, 6 becomes 1, 2, 7, 3, 1, 6. This is very important. The rank, I don't care. We're not going to talk about that. The inverse, you should be able to do an inverse. This is the formula for doing an inverse. Inverse is important for doing things like division. So just note, make a note to yourself, the formula for calculating the inverse of a matrix is on slide 49. So that when you get your midterm exam, you'll be able to do it. Trace, I'm not that interested that we do this. And eigenvalues, we certainly don't need to do that. We just need basic matrix algebra skills, okay? Calculating eigenvalues, we don't need that. Okay. This is the part that I want you to pay attention to. Well, this is the part that I want you to pay more attention to. Portfolio theory has a very big use of matrix algebra. And that's why I do this in this class, because I think it's cool. I think it's useful if you get a job on Wall Street or go to Chicago or Charlotte or wherever, one of those. So I'm going to spend probably the next, most of the rest of the class talking about how to do this, you know. And I feel like at first it may seem confusing. So maybe not, I don't know. It was confusing for me, let's put it that way. So it might take some review on your part over the weekend to try and figure out what it is we're doing, okay? But let's just jump in. Most important application of matrix algebra in finance is solving portfolio allocation problems. We have a set of N stocks that are included in a portfolio P with weights, W1, W2, Wn. Suppose their expected returns are written as the expected return of R sub 1, expected return of R sub 2. You could write the N by 1 vector of weights as W and the N by 1 vector of expected returns as ER. And you would have a vector of weights and a vector of expected returns. The expected return on your overall portfolio, ER sub P, would be calculated as the transpose of ER times W. So this is slide 53. I've got substantial notes that I would be writing on the board, but we don't have a board. So assume you have a portfolio with stocks S and bonds B. That's all, two things. With weight, as in percent of money in each, given by W sub S for the percent of amount of stock and W sub B for the percent of amount in bonds. Your return on your portfolio would be R sub P equal to the weight in stocks times the return in stocks plus the weight in bonds times the return in bonds. what we are saying on the slide here can be calculated as the transpose of expected returns of your stock times the weights is here. Your expected return is weights on the stock, is returns on the stocks, the returns on the bonds, and your weights are the weights on the stocks and the weights in the bonds. The matrix form would be the transpose of this, ER, times this, W. Imagine if you had 50 stocks in your portfolio, right? So you would have in Excel, you would have a column of weights, in other words, a percentage of your money, and the column of the return associated with each of those stocks. Yeah, and you would multiply them and sum them up, and you would have the return on your portfolio, right? Very straightforward, right? When it comes to calculating variance, it's not so straightforward because variance is different. A variance-covariance matrix of returns, denoted V, includes all the variances of the components of the portfolio returns on the leading diagonal, that's this, right? Sigma 1, sigma 2, sigma 3, and so on. And the covariance between asset 1 and 2, so sigma sub 1, 2, sigma sub 1, 3, the variance-covariance matrix may be written as V is equal to this. Okay? Let's come back to, I really wish I was sitting in a room with you guys and I could write this on the board and you could look and ask questions. Variance of a portfolio is a whole different ballgame because you may recall from statistics that the variance of the sum of two products, in other words, variance of AX plus BY, which is what you want up here, right? You just have stocks and bonds, yeah? The variance is A squared variance of X plus B squared times the variance of Y plus 2 times A times B times the covariance of X and Y. That's a rule in statistics, yeah? Recall the variance of the sum of two products. That's a rule. I mean, we can't get around it, right? But it's useful in portfolio theory. So we can construct a variance-covariance matrix which together with weights in your assets can provide the variance of your portfolio. This is very important. You've got 50 stocks. You want to know how risky is it, right? That's what this is all about. How risky is my portfolio? Am I likely to lose 20% on any given day? Or am I likely to only lose 3% on any given day? That's why this is important, yeah? And variance is very tricky when you put it all together in a portfolio. So we need to know what we're doing. So look, imagine if this is the formula to calculate the variance of the sum of two products, what if you wanted to calculate the sum of 50 products? Imagine how unwieldy this would be. It would be out of control. So we can do it in matrix algebra, right? I say imagine variance of AX, BY, CZ, and so on. And that's my eraser because it was windy. So on slide 55, let's go have a look at that. In order to construct the variance-covariance matrix, you first need to set up a matrix with observations on actual returns, not expected. Expected is the average of the past. Actual is what you're getting. For each stock where the mean has been subtracted away from each series. So you're constructing a matrix of returns. Yeah? The variance covariance matrix would then simply be calculated as R transpose times R divided by T minus 1. Let's make this bigger. Now, slide 55. I made copious notes in an effort to help you understand. Slide 55. You construct a matrix of actual returns, not your expected or i.e. average, and call that matrix R. So your variance covariance matrix would be R transpose times R divided by T minus 1. So this is in matrix format. So you have R, which is the return of stock 1-1, the return of stock 1-2, the return of stock 2-1, the return of stock 2-2. In other words, the covariance between 1 and 1, 2 and 1, 1 and 2, etc. The transpose of that is simply you swap the rows for the columns, which gives you the squares that you need in, a formula like this. So using this matrix of returns to calculate a variance covariance matrix, call it V. Notice we have divided by T minus 1. Why would we say T minus 1? Anybody have an idea? When you do variance in statistics and you do an estimate of variance, don't you divide by n minus 1? How come, Jack? What did we call it? What did Todd Moe call it, or Giles call it, or?
I don't remember the word for it.
A degrees of freedom adjustment. Oh, there we go. Jesse said it. You're adjusting, you're making a degrees of freedom adjustment because it's an estimate of variance. Okay? Just like if you had, X and Y, except now we have a matrix of stuff. Thank you, everybody. Let's go back. All right. So you want to calculate the variance of returns on your portfolio. You would have a scalar, which would give you a scalar, which is just one number, right? You want one number. You want to know my portfolio of 50 stocks has got a risk of 20%. Yeah, that's what you're after. That's what variance of portfolio, that's what we're talking about. What's the risk of your portfolio, right? So you want to know your whole portfolio is 20%. So you could calculate that by saying the transpose of my weights times the variance covariance matrix times the weights will give you one number, the variance of your portfolio. Let's look at my notes. This is slide 56. Slide 56. Use the variance covariance matrix V to calculate the portfolio variance V sub P using your weights W. Remember, you had a vector of weights, right, in each asset. Yeah, this is the weight in Apple. This is the weight in General Electric. This is the weight in Google. This is the weight in Facebook, right? This would be the the variance covariance matrix, or notice, why do we have sigma 1, 1, sigma 2, 2, sigma 3, 3? This is a covariance between asset 1 and asset 1, the covariance between asset 1 and asset 2, the covariance between asset 1 and asset 3. So when you do this multiplication, you're saying, hey, the covariance of asset 2 and asset 1 times the covariance between asset 1 and asset 2, that's simply saying the covariance squared, right? Or the variance, right? So the variance between asset 1 and asset 2. What's the variance between X and X? I mean, what's the covariance between X and X? It's simply the variance of X. Yeah? Okay, so we would have, i.e., variance of your portfolio is the transpose of W times V times W, where W is here, V is your variance covariance matrix, which we figured out up here, and W prime is just a transpose of W. Okay, so you can imagine how useful this is. You can imagine how useful this is if you've got a portfolio with several hundred stocks in it, right? The rest of this is a little bit more in depth than I want to go, but you could define a correlation matrix of returns, and then of course you could construct your variance covariance matrix by doing the same thing here using a correlation matrix of returns. But and then you could construct the portfolio with the least amount of variance, in other words, the least risky. Not necessarily the most optimal, but now you could also construct the optimal. And that tells you how to do that. I feel like if you guys can wrap your head around the things that I've just talked about for the last 50 minutes, that's enough. You know what I mean? And being able to do this stuff in matrix format is, for me, is very important that I get to see you do that. So I think you're going to need to spend a little bit of time playing around with this and looking over the slides, you know? But at the very least, I'm certainly going to ask you about how to do matrices and how to add and subtract and multiply them and stuff like that. So I think that's all I want to lecture about. I wish this particular section of the course where I review math, most of this is review. How much of this is review for you guys? I mean, for how many of you is this a review? So we started out with a little bit of review with y is equal to mx plus b, right? And then we ramped it up. And then you were like, oh man. Okay, so let's have a look at the problems associated with this, and that will take us to the end of the day. Oh, the variance, I have a question. The variance would be useful on its own. You don't need to compare it to a variance of a benchmark because, you're just looking at your portfolio, right? If your portfolio was, the question is, would the variance be a useful statistic on its own? or would you have to compare it to the variance of a benchmark? Well, most of us we have a portfolio catered to ourselves. If you were working for a Wall Street firm and they said, hey, I want you to construct an alternative energy portfolio and I want you to beat the benchmark, well, then you would need to look at that, right? But for us, all I want to know is that, my portfolio has only got like 6% risk. Yeah, in other words, I may only lose or make on any given day 6%. You guys should be happy to make or lose on any given day 18% because you're young, and wild. I'm like old and I got to hang on to my money, so I don't want to lose it all in one shot. But do you see my point? That's what this is all about. Well, that's a great question, Matt. Thank you. So I want us to go to the problems. Notice I put, I took pictures of it. I got numbers here. So we did these, right? Am I right? Did we do 7?
Yeah, we did.
So have a go at 21, A and B, while we're sitting here, okay? You guys have that up on your own computers, right? Can you put them up on your own computer so I could use my computer? Do we have any answers? You should see, all my neighbors are sitting on my front lawn in lawn chairs because this is so fascinating. They can hear me through the window. Do you ever go to the city and you see people watching the football game from the sidewalk on lawn chairs? Hey, I'm going to be at Bonaventure next week if anybody wants to say hello. Can't imagine. Can't imagine anybody would want to do that, but I'll be mostly in my office, I think. And any of you are most welcome.
When are you coming?
What?
When are you coming to Bonaventure?
Next week, all week, I'll be there. Monday through Friday. So what does anybody got for, which one was it?
I have one of them.
21A? Which ones are validly capable of being multiplied together?
I have one of them.
Which one?
The 1, -2, and then 6 and 4 pairs up with -3, 6, -8, and 4. I did that one. I multiplied those two.
Which one was they? Which ones were they?
Uh, it's A. I multiplied A and B.
A times B. Are there any others that are able to be multiplied?
C and D.
Which one?
C and D.
C and D. How about A and C? How about B and A? How about D and A? B and C? D and B? What's the rule?
Number of rows in the first one has to have the same number of columns in the second one.
I'm sorry.
It's not it.
No. The number of
Opposite way.
Yeah, you had it the opposite way. So listen, this is important. Here's how I remember it. Matrices are denoted by rows by columns. When you multiply matrices together, the columns of the first must equal the rows of the second. Yeah? Do you see how I do that little trick to help myself remember? And the result, don't forget, I did this, right?
You said it's the rows of the first and the columns of the second?
It's on slide 44. To multiply matrices, they must be conformable. The columns of the first must equal the rows of the second. The result is that the rows of you have a result of the number of rows of the first matrix and the number of columns of the second matrix.
So does that mean that A and C go together?
Yeah, there's 2 columns in A and 2 rows in C. Yeah. In B, there's 2 columns, and A, there's 2 rows. In D, there's 2 columns, and A, there's 2 rows. In D, there's 2 columns, and B, there's 2 rows. In D, there's 2 columns, and C, there's 2 rows. In B, there's 2 columns, and C, there's 2 rows.
I have a question. So you said that, so it worked for D times A, but it wouldn't work for A times D, correct? Because A has 2 columns, but then D has 3 rows.
Right,
Okay.
right.
And if it works like both ways, do we write it 2 times?
Well, the answers would be different,
Yeah, okay.
you know, because you're going down the row and across the column.
Okay.
Okay. Let's get out of here. What was the next one you had to do that I had up here? Anybody remember?
Just calculate 2A, 3B, and half D.
Sorry, I'm all confused right now.
I think it was 21B.
Oh, yeah. Okay, so you just had to do the multiplication, right? So in each of those cases, you just multiply that number by each of the elements of the matrix. Yeah? And what else? Oh, calculate the inverse. Did I say it was on slide 44? I told you to make a note. Anybody make a note? Right here. 1 over AD minus BC. Given given A, B, C, and D. A, B, C, and D. That's how you calculate the inverse. Okay. We don't have time to, I mean, you just follow the example. What I'm going to do is wait a few days until I post the answers so that you have a chance to play. Okay? Or would you rather I post the answers right away?
Yeah, post them right away.
Do you guys understand why this is important? When we have a portfolio of 50 assets, you're going to go out of your mind trying to figure these things out, right?
Did you post your handwritten notes as well?
What?
Did you post the handwritten notes you had for each slide?
Yes, I've already done that.
All right, speak. Thanks.
They are all up on Moodle so that you can go with them and look at the slides and the my handwritten notes.
Thank you.
All right. All right, everybody, we got to go. Have a nice weekend, yeah?
You too.
Yeah, you too, Professor. Thank you.
Thank you. Have a good night.
See ya.
Thank you.
Thank you.